Hello, my name is Marc Pfetsch and I will present a talk about solving mixed integer SDPs. So let me switch to the slides. So this talk is based on joint work together with Tristan Galli and Stefan Ulbrich, and the main source of the material I will present is the dissertation of Tristan Galli from 2019. Yeah, and it's about solving mixed integer SDPs. So what is a mixed integer SDP? It's the short for mixed integer semi-definite program. So it's an optimization problem of the form that you see here. So we are maximizing a linear objective subject to a constraint that is written here, where C is a symmetric n times n matrix, and we are subtracting a linear combination of symmetric matrices AI, and they are multiplied by variables yi, and the B is a vector in R to the M. So for each variable we get a profit, and some of the variables yi are required to be integer. So this is where the integer requirement comes from, and the variables that are required to be integer are collected in this set I. The constraint says that this matrix here, C minus this linear combination, should be positive semi-definite. So the symbol here says that the matrix is positive semi-definite. So this is equivalent to saying that all of its eigenvalues are non-negative, or if you multiply from the left and right with a vector, then this number that comes out is non-negative. So this is a very general class of optimization problems. In particular, we can include linear constraints and bounds on the variables, and also multiple blocks of such SDP constraints into this form here, and you will see some examples later. And the whole talk is about how can such problems be more or less efficiently solved. So this is the agenda. So I'll first show you some applications, examples, where this is important, and then solution methods. I will talk about duality in mixed integer SDPs. I will talk about the software that we are supplying and developing, Skip SDP. And then I'll very briefly discuss some topics that are relevant in this context, namely Skip SDP, dual fixing, and Warmstarts. And then I'll show you a comparison with other mixed integer SDP solvers, where you also see results of Skip SDP. I'll quickly talk about parallelization, and then I'll close with conclusions and an outlook. Okay, let's start with an application. The main motivation for developing Skip SDP was the robust Truss topology design problem. So here we are given n nodes in R to the D, and nf of these are free and the other ones are fixed. In the picture below, you see the fixed nodes here to the left, they are fixed to the wall, and the other ones can move, except that they are connected by m possible bars. So this is what we call a ground structure. These vertices or nodes are connected by bars that are stiff, and the black arcs that you see here are the possible arcs, and the goal is to select some of them and their thicknesses. And we should select them in such a way that a certain force F, which is a vector that applies to each of the free nodes. So df is the dimension d times the number of free nodes. And for instance, it's this blue arc here on the node to the bottom right. It pulls down, and we are supposed to construct the structure in such a way that it does not break down under this load. So more precisely, we are going to select cross-sectional areas of the bars of these black arcs. We should do it in such a way that the volume is minimized while still creating a stable truss, so it does not break down under load. The stability of this structure, so what stable means, is measured by the so-called compliance. It's 1/2 the inner product of this vector F, the force, times displacements U that happen under the load. So each free node under load will move a little bit, and this inner product multiplies it with the force that has the right dimension here. This compliance can be thought of or seen as the potential energy that is stored in the system, and this should be bounded. If it becomes too high, then the structure will break down. And here you see an example of such a structure. So we are selecting certain of these trusses, and we are designing the thickness of these, and they are chosen in such a way that the load here, the blue arc, is carried. Now, truss topology design problem is interesting because one can combine quite easily a robust optimization approach. And this is motivated by the fact that it might be that this ground structure or the optimal structure is very sensitive to changes in this load. So it might break down, so it might withstand a certain structure F that is given, but it might break down even if I change this force a little. And to somehow make the structure safe against such changes, one uses an uncertainty set that is written down here. So it's a set of loads F, and they are written as F equals a matrix Q times vectors G, which are bounded in Euclidean length. So without loss of generality, they are bounded by 1. This gives an ellipsoid, and so you get these red ellipsoids here. We have to choose the cross-sectional areas in such a way that the structure, the final structure, withstands each of these forces in this set. So it's robust against all of these forces. And one more extension of the original model is that we replace the cross-sectional areas X, which originally we were continuous, by a discrete set script A. So we only allow certain thicknesses or cross-sectional areas because they can only be manufactured with a certain given collection of discrete cross-sectional areas. And this then leads to the following model, which was originally proposed by Bental and Nemirovsky, and the extension to integer or discrete set of cross-sectional areas was done by Sonja Maas in 2013. So it's called elliptic robust discrete truss topology design problem. Elliptic from this elliptic uncertainty set with the matrix Q, robust because of the robustness, and discrete because we are selecting discrete cross-sectional areas. And so what do we see in the objective? We are now minimizing the volume. So LE is the length of the bar. And this sum here, so the X AEs are 0, 1 variables. They select a certain cross-sectional area for each edge or bar. And this complete sum here gives the cross-sectional area of the chosen one times the length gives the volume. The constraint here makes sure that we are robust against all the forces that are given by this set on the previous slide, where the matrix Q defined this uncertainty set. C max is an upper bound on the compliance that we are taking. This I is the identity matrix, and this matrix AX, so it depends on the cross-sectional areas that we are selecting, is the so-called stiffness matrix. It's written down here. It's a linear combination of certain matrices AI These are single bar stiffness matrices. They are actually rank 1, and they are multiplied by the cross-sectional area A coming from our script set script A, and multiplied with this binary variable xai here. So these variables are 0, 1, and we have the constraint that for each bar E, we select at most one of these cross-sectional areas. And as you can see, this is actually a mixed integer SDP. So this is one class of applications. The next application is quite different, cardinality constraint least squares. Here we are given sample points. They are collected as rows of a matrix A, which is m times d. So the sample points are in R to the d. And then we have measurements B1 up to Bm. So for each point, we have one measurement. And the goal is to minimize or find x in R to the d that minimizes this expression. So we are minimizing the Euclidean squared error between ax and b. And we have a regularization term here, which is the Euclidean norm times a scalar rho, which weights the two parts. This regularizes and can be seen as a certain ridge regression regularization. And moreover, in the set, so this is where the cardinality constraint comes from, we are restricting X to have at most K non-zero components. And then it was proved by Pilanci, Wainwright, and El Gaoui in 2015 that this can be formulated as such a problem. So we are minimizing tau and subject to this semi-definite constraint here, where diag Z is the diagonal matrices containing on the diagonal the binary variables Z. There are D of these for each component of X that we are selecting. And we have this cardinality constraint here that the sum of these ZIs are at most K. In fact, the ZIs are 1 if the corresponding component of X is non-zero and 0 otherwise. So this is another class of mixed integer SDPs. Our third application is or shows a quite classic connection of mixed integer SDPs to combinatorial optimization. It's the minimum K partitioning problem. Here we're given an undirected graph G with edge cost C and the number of parts K. And the goal is to find the partitioning of the nodes V into K disjoint sets V1 up to Vk, and such that the total cost within the parts is minimized. So we are summing over all the parts, K parts, and then we are summing over all edges that are within one of the parts, Vi, and we are summing up the costs. So here in the picture, you see such a graph. You see the weights on the edges and one solution. So this is for K equals 3. So we have 3 parts, blue, green, and red. And the cost of this is 1 because there's only one edge that runs within one of the parts, and it's this one here with weight 1. And the other parts do not have edges within their part. This partitioning problem has applications, for instance, in frequency planning in telecommunications and layout of electronic circuits. There's a formulation as a mixed integer SDP by Eisenblätter. It looks like this here. So we are minimizing this sum here subject to this semi-definite constraint. And the variables in the matrix Y are 0, 1. On the diagonals, we only have 1. And this matrix J is the all ones matrix. So all entries of this matrix are 1. And Eisenblätter proved that this actually gives a valid formulation for the K partitioning problem, which is not immediately clear, but required a little bit of thought. Of course, one can extend this model, for instance, by constraints on the size of the partitions. like here, if you add these linear inequalities, then there's a lower bound L and upper bound U on the size together with weights on each node. So this was our third application. Further applications, of course, exists. For instance, computing the so-called restricted isometry constants in compressed sensing, if you know what this is. In electric networks, there's the optimal transmission switching problem for AC power flow. And then certain robustifications of physical parameters, estimation problems in gas networks can be formulated as mixed integer SDPs. Subset selection for eliminating multicollinearity can be formulated, and many more. So I hope this convinced you that mixed integer SDPs is an important class of problems. And we are now turning to the question of how can such mixed integer SDPs be solved. And we begin with a very simple idea. One idea would be we somehow relax the SDP constraints, and then the remaining part is a linear program or a mixed integer program. And we are going to enforce the SDP constraints via linear cuts. So this can be seen as a cutting plane approach, similar to Kelly's method. In each iteration, one has to solve a MIP and then add cuts if the corresponding solution does not satisfy the SDP constraint. Yeah, the more advanced technique is the auto-approximation method, where again one has to solve MIPS in each iteration and then an artificial or additional NLP to proceed. I don't go into detail here, but these are the methods to do it. What one can do in practice is for general convex mixed integer nonlinear programs, one usually uses gradient cuts like this if the constraint is g of x less or equals 0. But in our case, this SDP constraint says the smallest eigenvalue is non-negative, so this means positive semidefinite. But unfortunately, this function, so that assigns to a matrix its smallest eigenvalue, is not differentiable everywhere. Instead, what we use is the characterization, so x is positive semidefinite if and only if this product here, u transpose times x times u is greater or equals for all u. And then what we can do if the matrix Z, which is this matrix C minus the linear combination for a given point y star, if this is not positive semi-definite, we can compute an eigenvector v to the smallest eigenvalue. So if it's not positive semi-definite, the smallest eigenvalue is negative. And we take an eigenvector v to that. And then we add this inequality to our current linear program. So this can be done by a linear relaxation. And this cuts off y star, and then one can iterate. So we actually are using this, and I'll come back to this later. Just a quick theoretical comparison between mixed integer second order cone problems, if you know what this is, and mixed integer SDPs. So for second order cone problems, cutting planes are often used in practice. Many solvers use an LP linear programming based approach, and one can use the auto approximation method that I showed previously or quickly mentioned. And one can actually show in order to reach a good approximation, one only needs polynomial number of cuts. Unfortunately, for SDPs, this is no longer true because Brown and others proved that one needs an exponential number of cuts to do that. So it will really depend on the particular instance whether an approach by these cutting planes will be worthwhile or not. And I'll show you later in the computational results that there are certain applications where it pays off and certain applications where it does not. The approach that we are going to follow is the SDP branch and bound method. So what we are going to do here is we relax the integrality constraints on the y variables, but we're keeping the SDP constraints. That means we are building a branch and bound node, and in each node we have to solve an SDP. So the node, the tree is created by branching on the y variables, so the integer y variables. We are solving an SDP in each node, and the relaxations in each node can, for instance, be solved by interior point methods or by other methods if you have can exploit particular structure. One downside of this approach is that we have to solve this SDP in each node. So we somehow have to satisfy the convergence assumptions of the SDP solvers. And this is what we are going to discuss next. So it's a section overwritten with duality and mixed integer SDPs. And the question is really, so if our root SDP in the root node has nice properties so that it can be solved by interior point methods, will the same be true for the nodes in the tree if we are branching or adding cuts? So to motivate the question, let's us look at the pair of dual SDPs that are written out here. So the form that I showed you in the beginning without the integrality constraints is what usually it's called the dual SDP. So we are maximizing linear constraints subject to SDP constraints here for a vector y. And the corresponding dual problem, the primal, looks like this here. It's very similar to LP duality. So if we are maximizing here, we are minimizing. The objective is to minimize this product here. It's an inner product of the matrix C with a matrix X, and it's written down here. So it's just the sum of the products of all entries. C can be seen as the right-hand side of this constraint here. So it's the right-hand side times our variables. And then we have the product of the matrices AI with the vector X and should be BI. So the objective becomes the right-hand side. And then we have the constraint that X, the matrix X should be non-negative. So a little thought shows that these are actually dual problems. And one can derive certain results for these pair of dual problems. For instance, strong duality, that means the objective values of these two problems are equal. This holds if Slater condition if the Slater condition holds for the primal or the dual. So in the primal Slater condition means that there is an X that is actually positive definite. So X is positive definite. In the dual, it means there's a vector Y such that this matrix here is positive definite. So one can say that there exists a solution in the interior of the constraint set. The Slater condition implies strong duality. And it also says if it holds for P, then the optimal objective of D is attained and vice versa. So if the Slater condition for D is satisfied, the optimal objective of the primal is attained and vice versa. So it might be for these problems and different to linear programming that the optimal value is not attained, but there's only a sequence of points y that converge to the optimal value. This is why I've written here a supremum. And similarly for the primal, I've written the infimum. So the optimal value might not be attained, but there is a sequence of matrices xi that converges to the value of this problem, to an optimal solution, so to say. Now, for interior point methods, it's important to have so-called KKT points. And the existence of such points is guaranteed if the Slater condition holds for both problems. So contrary to strong duality holds if the Slater condition holds for either or the primal or the dual. For KKT points, we actually need both. This is a relatively strong requirement, and only if this is satisfied, the convergent theory of interior point methods will work. And now we come to the basic question of this section. The question is if the Slater condition holds for the primal and dual for the original root SDP. What happens if I branch on the y variables? That means I'm adding bounds for the y variables, or if I add bounds to the x variables here. Can it happen that we are losing these nice conditions, the Slater conditions, or can it be that we might not even have a KKT point? So there we obtained the following theorem. So let D plus be the problem that is formed by adding a linear constraint. That means to the dual, and that means that we are generalizing what is happening in branch and bound. So in branch and bound, we are adding bounds to the y variables. And here the theorem is about adding any linear constraint. So adding a bound, of course, is a special case of this. So now, if strong duality holds for the primal and the dual, so their objective values are equal, and the set of optimal Z matrices of this form in the dual is compact and non-empty. Moreover, this problem D plus with the additional linear constraint is feasible. Then strong duality also holds for our dual D plus and the corresponding dual that is called P plus. And the set of optimal matrices Z for this new problem D plus is compact and non-empty. So this property being compact and non-empty is retained. So now Freeberg showed that compactness of this optimal set Z is necessary for strong duality. If this does not hold, then it's not necessarily a strong, we don't have strong duality. And we can prove analogous results for adding linear constraints to the problem P with a set of optimal matrices X that is compact and not empty, and the corresponding problem being feasible. So this says at least strong duality is inherited in the tree. So if I add linear constraints and the conditions are satisfied, then all of the SDPs in the nodes deeper down in the tree also satisfy strong duality. So here is a theorem about, or a proposition about Slater's condition. So it says the following: if we add a linear constraint like this on the y variables to the dual, so I'm adding a linear constraint to the dual, and the primal satisfies the Slater condition, and the coefficient vector A of this linear constraint is in the range of the linear operator A that is given here. So the linear operator maps from the symmetric n times n matrices to R to the M, and it maps the matrix X to the M inner products AI times X. So this gives a linear operator, and if A is in the range of this linear operator, then Slater's condition also holds for the new primal, the dual of the problem D plus that we get here. So this condition A in the range of this linear operator is already implied if the original matrices AI are linear independent. So it's not too harsh restriction. The dual Slater condition is preserved after adding such a linear constraint to P. So this is the analogous result. And there we don't need this additional restriction that A is in the range. So this is a positive result. So by adding linear constraints, we inherit Slater's condition under the condition of this propertization. So let's discuss some concrete examples, namely an example that shows that KKT points may get lost after branching, which is unfortunate because we need KKT points for interior point methods. So let's look at this primal and dual pair of SDPs. So it's 2 times 2. If one looks at these problems a bit, then one sees that there's a strictly feasible solution given by y. So the first component is 0, the other one 0.5. And there's also a strictly feasible solution for the primal, where the matrix, the only non-fixed variable x11 is 2. So if you plug those in, then you get a positive definite matrix here and here. The optimal objective is 0.5, and it can only be obtained for y being 0.5 in each component, and x11 being 1 here for the prime. So in this case, strong duality holds, and in fact, the optimal values are attained by these 2 points here. Now imagine we are branching on the variable y2 by adding the cut y2 being less or equal than 0. And adding the cut means we have to add one more variable, a slack variable for this inequality. This produces a 3 times 3 matrix here in the dual and in the primal as well. So these are the new problems if you think about it for a while. And here the optimal objective is actually 0, and it's attained for the dual by y being equals to 0, 0. So for the 0 vector. Unfortunately, the relative interior of D plus is empty, so it does not have interior an interior, and there does not exist any values of y1 and y2 being equal to 0, of course, that is positive definite. So we are losing this strict feasibility. The problem P plus here has a strictly feasible solution, which is given by this. So here we still have a positive definite matrix. This P plus has the property that the optimal objective is not attained, but there's a sequence that converges. It looks like this for k going to infinity. And this means, that it does not have a KKT point. It only has a sequence that converges to the optimum. So it cannot have a KKT point. And this means that it does not satisfy the assumptions for convergence of interior point methods. And this means you can run into algorithmic trouble by solving such a problem with branch and bound. So let's look at this in practice just to get a little impression. So what you can see here is 3 applications, and whether the dual Slater condition or the primal Slater condition is satisfied for the corresponding node problems that are solved when solving the mixed integer SDP. And you see that the dual Slater condition is not always fulfilled. So this is this first column here. The second column says if it's not fulfilled, and then there's a certain percentage where the corresponding SDP is infeasible, and there's a certain number of cases where we don't know. So the solver does not say whether it's feasible or infeasible. For the dual, that means the dual Slater condition is rather often not fulfilled, but the primal is very often fulfilled. But sometimes, very seldomly, the interior point method cannot conclude whether the problem is feasible or infeasible. Here we're using Mosaic as an SDP solver. So what can be done if we run into trouble? Obviously, it happens from time to time. If you, by the way, change the SDP solver to other ones, then this happens more frequently that we run into the situation where we don't know. Here we can solve this so-called feasibility check SDP, which was suggested by Sonja Maas. It's an artificial problem where minimizing this slack variable R, which we are adding multiplied by the identity matrix I here. So if the optimal value of this SDP here is positive, then the original problem is infeasible because we could not make R to be equal to 0, which would say that the original problem is feasible. If this is the case, we can cut off the node. Then if the problem is not infeasible, then we solve a so-called penalty formulation, which looks like this. So we are again using this slack variable R, but we are supplying it in the objective with minus coefficient gamma times R. And the gamma should be large enough to compute an upper bound on our original relaxation. Now, if the optimal value of this SDP here is 0, then the solution is also optimal for the original problem, because then, yes, so this term here vanishes and we are feasible. If it's not 0, the R optimal R star, then we can add a constraint that the trace of the matrix X is at most gamma to the primal problem. And if gamma is large enough, then this preserves Slater's condition. And so this problem here fulfills the Slater conditions and is therefore hopefully solved by interior point methods. So in this way, we can handle the cases where the solvers not by themselves handle or decide feasibility or infeasibility automatically. So, and here you see the results. So what happens if Slater's condition holds for the primal and the dual? Then you see for different solvers, so one SDP-A is one solver, DSDP and Mosaic. And you see that Mosaic is very stable, DSDP in default also, but SDP-A not so much. We have to often run the penalty formulation to decide, and very seldomly this bounding SDP. And in some cases we are unsuccessful, then we have to somehow recover within the tree by solving an LP or branching. So if the Slater condition fails, then the success rate decreases. It decreases significantly for SDP-A, but not so much for the other two. And if the problem is infeasible, at least DSDP and Mosaic are usually successful in deciding it, but very often we need the penalty formulation to decide. And then even sometimes we need this bounding SDP to decide whether the problem is feasible or unfeasible. And there are still certain cases where we are unsuccessful, but not for Mosaic, luckily. Okay, so the conclusion of this is that theory says that often the Slater condition is satisfied in the nodes, but not always. And in practice, this is true, and you can see the effect on the interior point solvers. So usually they work fine, but then from time to time, they fail to correctly decide whether a problem is feasible or infeasible. And then we have to apply this penalty formulation or the bound formulation to recover most cases at least. Okay, let's come to skip SDP very quickly. So skip SDP is based on the skip framework, which you should know by now. It supports both nonlinear branch and bound and LP-based branch and cut. It has file readers for two formats, the so-called CBF format and the SDP-A format. It implements a so-called constraint handler for SDP constraints. It interfaces to 3 SDP solvers. You've seen them already: DSDP, SDP-A, and Mosaic. And it has primal heuristics, diving-based heuristics, and randomized rounding. And it has propagators, optimality-based bound tightening, and a dual fixing method, which I'll show you in a second. There's a parallelized version available, which I also will quickly mention later. And it supports rank 1 constraints, which are implemented together with Frederic Matter. So the constraint handler handles SDP constraints of this form, which you've seen. It can use branch and cut. That means it can use LP-based branch and cut and generates these eigenvalue cuts. And it can do certain pre-solving in the beginning. So for instance, the diagonal entries of the total matrix have to be non-negative to be positive semi-definite. And one can add certain linear constraints that are redundant for the SDP, but can help to do pre-solving. And this leads to a speed of about 6%. Then there's a relaxator, which solves the SDPs. So it has an interface to the SDP, so that's SDP-I. It takes care of certain special cases. For instance, if all variables are fixed, or if there are fixed variables, then they are removed. If there are 0 rows and columns, they are removed. All this is important for most SDP solvers because they would break down otherwise, which is maybe a bit surprising in the first glance, but this is how it is, and the relaxator takes care of this. The lower level SDP-I brings the SDP into the form needed by the solver. And then if the SDP solver fails to converge, then it applies this penalty formulation and the upper bounding SDP. Okay, so now you've seen some theory and practical ideas of how to deal with infeasibility or feasibility if the interior point method solvers fail. And now we are going very quickly to some techniques that are applied within skip SDP. The first is dual fixing. It's an extension of the so-called reduced cost fixing. It was generalized to general min-LP and primal mixed integer SDPs, and our approach is based on conic duality and only requires feasibility. So what's the idea? I don't want to go into detail, but the idea is, so for the primal, we have variable x, w, and v, where w and v are primal variables corresponding to bounds in the dual. So, and the bounds that we have are L and U. So for the y variables, we have a lower and upper bounds. Then f are variables, is the value of primal solution. So it's the objective value of a primal solution. And we have a lower bound on the optimal objective of the mixed integer SDP that may come from a relaxation or within the tree this is available. And then we have the theorem that for every optimal solution y star of this mixed integer SDP, these inequalities here hold. So if the lower bound is not minus infinity, then the jth component of the optimal solution is bounded by the lower bounds plus the upper bound minus the lower bound divided by the diagonal entry in this matrix W here. And for the upper bounds, a similar inequality holds. This is particularly useful for if y is actually binary, because if f minus L is less than this diagonal term, so this here is less than 1, then we can actually fix the corresponding y variable to 0. And conversely, if f minus L is less or equal to the diagonal of this V matrix, then we can fix the y variable to 1. So this reduces on average the number of nodes by 9% and leads to a 23% speed up in the solution of mixed integer SDPs. Then Warmstarts. So for MIPS, one of the key components to success is hot or warm starting, because the dual simplex can start from an optimal basis of the previously solved LP. For interior point methods, this is not so easy, although one can start with a point, which is hopefully close to the optimum and then hopefully converge faster. But this is not nearly as easy as for the simplex algorithm. So the goal is to choose starting point for the primal X and for the dual Z that are positive definite, so that actually show that Slater's condition is satisfied, and start the interior point method from there. So one has to somehow construct these points, and there are several methods to do so. So here are some of them that are collected. So one would be we start from earlier iterate. So we don't solve, or we store a point when solving with the interior point method that is not yet optimum but close, and we are storing that because that is in the interior. Or we can take a convex combination with a strictly feasible solution, or we can project onto the positive definite matrices. So this can be explicitly computed by an eigendecomposition method, or we can round. So this works as following. We fix the eigenvectors of the parent node and optimize over the eigenvalues. And if you look at this a bit, then you recognize this is actually a linear program. And by solving this LP, it's a relaxation, so you can actually sometimes decide optimality or infeasibility. And you can use the solution of the LP as a starting point of the Warmstarting. But still, the solution needs to be adjusted a bit for strict feasibility. So these are 4 methods for Warmstarting. And here you see some results. There's a lot of numbers. And the bottom the bottom line of this table is, so no Warmstarting solved 288 instances, and there's only one method to solve more. It's this here. So this is convex combination between the identity matrix and the positive definite matrix. It saves a bit of time, but the savings are not really great. And remembering that I said it's very difficult, maybe these are not surprising. But if you now look at the results for the different applications, so for Truss topology, constraint, cardinality constraint, least squares, and the partitioning and the restricted isometry problem, then you see that for some cases we actually get a speed up. So if there are negative numbers, we get a speed up. And for some, we get slower. And for projection, we are mostly getting slower. But for the RP application, we get faster. So it's a mixed table. And this means for certain application, it might be very well feasible to use Warmstarting, and we get a speed up of sometimes up to 30%. Okay. Let's now look at the comparison to other mixed integer SDP solvers and some results. So skip SDP uses nonlinear branch and bound, and for the computation we use skip SDP 3.11. And we compare with YALMIP. It's a MATLAB toolbox for rapid prototyping. I have to say that this is not tuned for performance, although in the recent years this has been improved. And then one can also apply this outer approximation idea, LP-based approach, which is also supported by skip SDP. And YALMIP has this as well. And there's Parahito, a new solver that allows this as well. Here are the results in the performance diagram. So the y-axis is the number of instances that are solved, and here's the time within 1 hour time limit. And we see that skip SDP with nonlinear branch and bound is the best. It solves the most number of nodes, but in the beginning, it's a bit slower than other versions. Skip SDP that uses LPs is quite good as well. It's a bit faster in the beginning, but solves less instances. YALMIP branch and bound, nonlinear branch and bound is very good, but not as good as skip SDP. Yeah, YALMIP with LPs is quite bad, and Parahito is relatively good. So if we look a bit into detail on the different applications, so Truss topology, cardinality, constraint, least squares, and partitioning, we see that for the Truss topology, skip SDP with nonlinear branch and bound is best. For cardinality least squares, the LP approach is actually the fastest. But Parahito is, of course, good at it as well because it uses LP branch and bound. For partitioning, again, nonlinear branch and bound is best in the number of solved instances, but YALMIP is a bit faster. And overall, skip SDP solves the most number of nodes with nonlinear branch and bound and is the fastest on average. Finally, just a very quick comment on parallelization. So there's a parallelization that is available. It's based on the UG framework. One can either parallelize the SDP solving within the nodes, or one can do it on the MIP side, so parallelizing the nodes. Unfortunately, parallel Cholesky decomposition that is needed for the SDPs, for solving the SDPs, depends on the sparsity pattern, and it is often only successful for larger SDPs. And for mixed integer SDPs to have hope to solve them at all, we are usually small. So we don't really benefit from solving the SDPs in parallel. Now, this is why it's concentrating on solving the subtrees of the branch and bound tree in parallel. This is, of course, not possible for the root node. So it uses the concept of the racing ramp up, where it solves the problem with different, or the root node with different settings, in particular using the LP or SDP. And then it selects the best settings in the nodes to come. So it starts a number of skip SDP instances in parallel, and half of them is using LP-based approaches, and half of them the nonlinear SDP-based. And after enough nodes have been generated, it decides on the best solver and then uses this setting for the remaining of the tree. So here you can see some results. So skip SDP in serial, and then UG mixed integer SDP with 1 up to 32 processors or CPUs for the different applications again. And we see the most number of nodes is still solved by the serial approach, but you get a bit faster if you, for instance, use 16 CPUs. You somehow have the time, which is clearly not an excellent speed up, but at least it shows some success. Okay, so let me come to the conclusion and outlook. So I hope that you got an impression of how to solve general mixed integer SDPs. I tried to highlight some components. Of course, this was very quick, and I'm inviting you to read more in the publications or ask me. It's an interesting class of problems that I think will gain importance in the future. Several methods help to improve the performance. Remember that our approach was to solve general mixed integer SDPs, so it should work for any mixed integer SDP that comes around. Solving the SDPs is still the main bottleneck here. But often these SDPs provide strong bounds, so you get much less nodes comparison to an LP-based approach. For the future, we plan, we hope to follow the development path that has applied for mixed integer linear solvers in the past decades, where there was a tremendous speed up, and the hope is that we somehow can mimic this for mixed integer SDPs as well. So Skip SDP is available at this website here if you want to download and play with it. And with this, I thank you for your attention. And at the end here, there are some references if you want to read more. The most comprehensive is probably the dissertation of Tristan Galli. Thank you.